Today, thousands of businesses use advanced machine learning and AI to gain future insights. Hi there, I'm Tobias Zwingmann, AI expert, author, and former senior data scientist. In this course, I'll guide you through the first steps of time series forecasting using Python and AI, so you can apply them to your business. Make no mistake, this is a complex field, and you certainly can't become an all-knowing oracle in the next couple of hours. But with my help, you can apply the main building blocks to hone your forecasting skills in batch, near-time, and real-time scenarios. So if you're ready, let's dive in. Blocks of doing AI-powered time series forecasting. You will learn how to transition from batch over near-time to finally real-time forecasting, and you'll get to know when to use which approach. At this point, let's also briefly discuss what this course does not cover. Be aware that this isn't a beginner course to doing machine learning. There will be some prerequisites, which I'll cover in a second. Also, this is no regular time series course in the sense that we won't be covering techniques like ARIMA or other models that are typically used in time series forecasting. Instead, we will see how we can use more advanced AI and machine learning models to do time series forecasting for us. And finally, this course isn't designed to be an academic curriculum. I designed this course from a very practical perspective, which also means I had to leave a lot of stuff out to make it fit into the given scope. I tried to make the building blocks complete so you can dive deeper if you want, given the resources I provide for you throughout this course. So to get the most out of this course, there are a few prerequisites. First, you should have a basic understanding of Python programming. Second, you should also be familiar with the fundamentals of machine learning. If you've never heard of concepts like training, testing, or feature or target before, then this course might be too advanced for you. Consider taking a machine learning crash course before. I'll quickly walk you through it, and it's super easy to set up. What GitHub Codespaces is doing is setting up a virtual environment for you right in your browser, so you don't need to install any of the dependencies from that locally. So how do we get started with Codespaces? Log into GitHub and navigate to the course repository. From here, click on Code and create Codespace. When creating the codespace, GitHub will automatically fork the repository for you, so you can commit changes later on to that repository. If you're setting this up for the first time, this will take some minutes to load. If everything is set up, your codespace should look similar to this. Let's close this README file for now. This repository has branches for each of the videos in the course. You can use the branch pop-up menu here to switch to a specific branch and take a look at the course at that stage. The branches are structured to correspond to the videos in the course. The naming convention is chapter number _ movie number. As an example, the branch named 10_12 corresponds to the second video in the first chapter. You might find that some branches contain a B and an E naming convention at the end. Branches that end with B mark the beginning state of a certain video. And when the branch ends with an E, that marks the end code state of that movie. The main branch of this course is empty. So let's try it out. Let's say you're starting to watch the second video in the first chapter. Open branch 01, 02, and B because there's an end state here. So in this branch, you will see that there's now a new folder here on the left side. And in that folder, there's also a Jupyter notebook where you can code along as you like. One final remark. When you're working in these files like this, and you want to Throughout this course, we'll be using the same AI model. You might be wondering, what exactly is an AI model? Let's break it down into two components, AI and the model. First, let's discuss what AI is real quick. The term artificial intelligence, or AI, has been around since the 1950s. If you heard about Alan Turing before, that's roughly where AI dates back to. There are two types of AI: general AI and narrow AI. General AI aims to solve any problem that the system has never seen before, but that's still mostly in research phase. Narrow AI, on the other hand, focuses on solving specific problems. And that's what really powers all the business AI applications today. Machine learning has enabled the latest breakthroughs in narrow AI. The core idea behind machine learning is to find patterns in historical data and exploit these to solve specific tasks. Deep learning is a particularly complex form of machine learning. And with machine learning and deep learning, we can achieve 5 main archetypes of AI capabilities: supervised machine learning, computer vision, natural language processing, audio and speech, and generative AI, which are AI capabilities applied to different types of data. In this course, we will primarily focus on supervised machine learning. However, later in this video, you'll also explore the exciting area of generative AI. Now, let's dive into the specific model we'll be using, XGBoost. XGBoost stands for Extreme Gradient Boosting. It's a powerful and popular machine learning algorithm. XGBoost is widely used for structured data and tabular datasets. It excels in tasks like classification, regression, ranking, and even time series forecasting. XGBoost has several key features. It's an ensemble method based on decision trees, specifically gradient boosting. XGBoost is designed for speed and performance. It offers regularization to prevent overfitting, and it supports parallel processing for efficient computation. At a high level, here's how XGBoost works. It builds an ensemble of decision trees iteratively, and each tree corrects the errors made by the previous trees. XGBoost minimizes a regularized objective function. This function includes a loss term and a complexity term. It uses gradient descent optimization to minimize the objective function. You wouldn't believe it, but XGBoost is particularly well suited for time series forecasting. It can capture complex patterns and relationships in time series data, and it can handle various types of time series, including univariate and multivariate data. It's also robust to individual outliers, and XGBoost provides built-in feature importance scores. Finally, it offers hyperparameters for fine-tuning and optimizing performance. We won't dive too deep in here, but here's a set of key hyperparameters that you can tune in XGBoost, among many others. N estimators, which determines the number of trees in the ensemble. Max depth, which sets the maximum depth of each tree. Learning rate, which controls the step size shrinkage used in updates. Subsample, which specifies the fraction of observations to be used for each tree. And call sample by tree, which determines the fraction of features to be used for each. They are pre-computed aggregations and transformations of raw data. Batch features capture high-level patterns and relationships in the data. They are commonly used in machine learning and AI models, so they are not exclusive to time series forecasting. Ultimately, batch features help improve the model performance and efficiency. Why should you use batch features? They provide more informative representations of the data. Batch features capture domain-specific insights, and they improve accuracy and generalization. Batch feature processing allows handling very large datasets. And there are actually different types of batch features. For example, aggregations like sums, means, max, or minimum values. Statistical measures like standard deviations and percentiles. And of course, especially in time series forecasting, we use features that include rolling computations and lag features. But besides that, we could also use categorical encodings, such as one-hot encodings that are really common. Or we could bring in domain-specific features to capture unique aspects of our data, like marking holiday seasons, for example. Creating batch features involves several steps. First, identify relevant aggregations and transformations. Then we use data manipulation libraries like pandas or SQL to compute batch features on a regular schedule, such as daily or weekly. We can store batch features in a feature store or a database to ensure data quality and consistency. Using batch features in AI models is pretty straightforward. We persist the features in a feature store to use them as input for our machine learning models. If necessary, we could even combine batch features with other types of features, like real-time features, but we'll get to that later. Generally, it's not the more features the better, but we need to closely evaluate the impact of our features on our model's performance. And finally, we have to monitor and update batch features over time to handle things like concept and data drift. If this sounds a bit too overwhelming, don't worry, we'll get there. Especially the last chapter of this course will be really focused on model evaluation. Here are some So first, on the left side, you will see the folder here, batch. And inside batch, you will find a txt file called code along. So every code that I'm using in this video will be coming from here. And if you want, feel free to just follow along and copy the code from here, and then we can go through the whole thing step by step. All right, so to start off, let's open our notebook called featurescalculation.ipynb. So what are we actually doing here? Let me give you some context. Imagine we are a utility company providing energy to New York City. Every day, we want to accurately predict the energy demand for the next 3 days so that we can optimally plan our resources. And in order to do that, we will look at historic energy demand data and create batch features that we can use to predict the future energy demand. All right, so without further ado, let's go. Prerequisites. First of all, let's import pandas. That's the package we will need to create our features. And then on the left side, you will see that I provided some energy data over here in the data folder. So what we're going to do first is to set the file path to this CSV file. Just copy that over here, run this command. And then just to give you a quick heads up, this is actually not an academic data set. It's a real-world data set coming from the US Energy Information Administration. And if you ever find yourself in a place where you want to update the data or get the latest energy data for New York City, just copy this code here, which will basically fetch the data from the online API of their website. You'll need to go through this website, eia.gov, and register for a free API key, which you need to specify here, and you can update this data. I will work with the static data set for here, but just to give you some context that this is actually coming from the real world. Okay, so let's take a look at how this data set looks like. Just copy this one over here, where we just read the data into our data frame in pandas. And you can see that what we have here is a data set of hourly energy demand data from the city of New York, where the main thing that we're interested in is the value here in megawatt hours. That's the consumption for this given hour for the city of New York as described or as provided by the EIA. And you can see in total, if we just remove this one real quick, we'll actually have a lot of rows to cover. So these are 2,000 rows, and this is an energy data set spanning January 2024 up to the latest entry here is March 30th, 2024. Okay, so next is that we're going to aggregate this data by day because we want to calculate the data, the energy demand for the next 3 days. So we want to have it on a daily basis. And I'll just run this resample code here from pandas to get the daily data. And you can see now we suddenly don't have 2000 rows of data anymore, but just 90 because we just have 90 days of data. And then we aggregated every value by the sum for each day. So let's take a look at this data. As you can see, this is a more or less classical time series data set. So we have some trends going up and down here, and also a overall trend rather going downwards here over the past 3 months. But without diving too deep into the intricacies of this time series data, let's imagine, or let's think about what kind of features we can calculate in order to model this data set or this time series data set to forecast the future demand. So what I did was something which is quite common in time series forecasting, which is creating lagging features. So lagging features are essentially features that summarize data on a given historic time window. So I copy this one over, and then I'll quickly go through it and probably make more sense once you see what's happening. So what this code is doing is that we create now new columns for different lags of data. So this one here is a feature which calculates the energy demand from a given previous date. This one here, lag 4, is another lagging feature. And what this does is it creates a lag of data for the energy demand of the next 3 days, but minus 7 days. Because why are we doing that? Imagine we want to forecast the energy demand for tomorrow, the day after tomorrow, and the day after that. It might be worth looking into what was the value of 3 days from tomorrow, but 1 week ago. And this is what this data is, what this shift is doing. So this lag of 4, 5, and 6 is giving us exactly this reference in time. And we also do this here for a lag of 11, 12, and 13. So this is the same, but just for 2 weeks. So we just take a look at tomorrow, but 2 weeks ago, because that might be a valuable predictor of what's going to happen tomorrow. So let's see how that looks like. And you can see that at the beginning, there are a lot of missing values here, which totally makes sense because in order to calculate these features, we need to have at least a minimum offset of data of 14. So the first point in time that we can actually calculate these features for this data point is on day number 14, because before we didn't have the lag 13 available, right? You see that? So after 14 days, that's the first time we can really calculate these batch features for the lagging data set. Okay, so what else can we do? Another typical thing that you do in time series forecasting is to calculate so-called rolling statistics. So let's copy that over here and I'll quickly explain what this one is doing. So this is a rolling mean of 7 days, and this is a rolling mean of the standard deviation of 7 days. So that's pretty straightforward. And as you can see, we have this first after 7 days because we need 7 rows of data, 7 observations in order to calculate the rolling mean and the rolling standard deviation. So now that we have that, let's take a look at our actual target, at the stuff that we want to predict. And truth be told, we actually have 3 targets here, not just 1. So let me paste that in here. And what this code is doing is that we now take a certain point in time, a certain date, but we model the next day as our target. So let me show you an example. If we run this code, you can see that, for example, this one here, January 14, 2024, the targets for the next 3 days are this one. This is the target for the next day, which would be January 15. And this will be the target date for January 16 and January 17. So these are essentially the energy demands for the next consecutive days for January 14. So this is essentially the feature data set that we have on a very high level and general basis. And if you just wonder how these targets look like in the actual data set, you can compare those here, right? So you can compare these values and just check that these are basically in line with the targets that we have over here for the next 3 days, right? So 128, 866, 131, 883, and 131, 606. These are exactly those targets for the next 3 consecutive days, given that in this case, this will be the 1st of January. All right. I'm just taking this time to understand because it's very important to understand how this data is structured and what we're actually trying to do here, because we're now taking the time series data that we have and breaking it up into regular features that we would normally use in order to build a machine learning model. All right. And with that being said, let's drop all the missing values from our batch data set, because we can just work with those where we have these lagging features available and where we have the targets available. So in this case, just dropping the features here, missing features from the static batch data set. And also, let's inspect how these actually look like. Because you might be wondering, why are we exactly taking these kind of features? And that would be a good question. And the answer to that is, well, because we saw some correlation in here. And I'm going to close that one so we have more space here on the screen. Our features, of course, we want to store them somewhere. And this is how we do it. First of all, please take a look at this code along file again. If you want to follow along anything that I'm doing here, open this file and you can just copy and paste the code that we are using for this demo here. All right, so let's jump into our notebook, which in this case is called features storage.ipynb. And what we're going to do now is to build a really simple feature store for our batch features. So first, let's insert this code cell, and then from our code repository, we just copy the necessary libraries, execute those. Beautiful. We go back to our code repository, and then we set up our feature store. So these are some lines of code. I'll just copy them, and then I'll explain them what they do. So what we do here is we define a dictionary where our features should be stored, and this dictionary name is feature store, and then we define a so-called YAML file. The YAML file has an ID, and the overall goal of our YAML file is to save as a storage that describes our feature store. So It points to an ID of the feature store. It also has some information about when the latest feature was added and also when the latest target variable was added. It also gives an idea about the feature offset, so the minimum amount of data that we need in order to create one feature, and the target offset, so how many days ahead is our target variable. And then it specifies the path to where these features are stored. Quick heads up, normally you would not store that as a CSV file, but in some kind of other blob storage format or probably in the data warehouse. But to keep things simple here, we'll just use a CSV file. And then we also specify our schema, which is what kind of features, what kind of variables are we expecting here and storing in which kind of format, and similarly for our target variables. And then we have some code which defines the file path to this YAML file, and then finally we write this config dictionary to our YAML file. So if we run this code, you can see that there's a new dictionary being created, feature store, with the config YAML inside, and this is how the YAML file looks. Great, now we have the skeleton for our feature store available, and we just need to populate it with some actual data. And to do this, I go back to the code along file, and I'm going to import our feature processing script from the earlier video. So we go back to our notebook, we paste that in, and then put our code here. We run this, and as you can see, beautiful, this is our feature pipeline being executed and our set of features over here. So how do we store those? We need to write a little function that now actually takes all the information from the YAML file and then executes the storage operation. So go back to the code along file, and you will find some code over here which is exactly doing that. So let's copy this over. And this time we're not copying that to the Jupyter Notebook, but to the feature_store.python file, which will be a placeholder to manage and store all our our logic, our functions that are required to interact with the feature store. So we paste that in here. I'll just give you a quick walkthrough of what's happening. So we load the YAML file. We specify the file path for our features. Then we update the field when the features got updated, and finally write everything back to the YAML file. Pretty easy, pretty straightforward, but also a very simplified example. So back to our notebook, and we want to include this function now over here so the features actually get stored in our feature store. So I head over to the code along file, and I copy this code to update the feature store. Go to the notebook, paste it in here. And quick heads up, before you can actually run this one, you need to add the import command, because right now the notebook does not know what this feature store function is. So in order to do that, you will type the following. You will say from scripts import feature store. And this will import all the functions from that Python file. And before the Jupyter Notebook can actually access it, we need to restart it. So we restart the notebook, and then we can say run all. And as you can see, our feature update feature store function got updated, got executed, and the latest feature available is now March 30th. Great. So next thing that we want to do is to access data from our feature store. So head over to the code along file, and you will find a new function, fetch data from store. Copy the whole function, go back to the feature store.py, scroll down, and paste it in here. Again, what this function is doing is really simple. It takes an optional argument, period, and it needs to have a YAML file. And the YAML file gets loaded. And from the YAML file, we extract the file path to our features. We load the features. And if necessary, we fill the features by a certain period. Okay, great. Back to our notebook. And we want to insert the code over here. And to get the code, we go to our coding file, XGBoost to predict the next 3 days of energy demand. We will do some data wrangling in the beginning before we dive deeper into the mechanics of training the model. Let's open our file training.ipynb and insert a new code cell. Heading over to our code along file, we can copy the first rows of data and paste it here, simply importing our YAML file and making it available for the notebook. Next up, let's get some features. We copy this code, paste it in here, and thanks to our work from the previous videos, it's really easy to get the features for our training dataset. Just a quick heads up here, we skipped the last 7 rows of data, so we save some data for later demo purposes on examples that the model has never seen before. All right, let's go down and we have our features. What we need next is our targets. So let's copy this code and also retrieve our targets in a very similar way. There you go. These are our target variables. What we want to do next is we want to be able to update our feature stores also with the target variables, because in the last video we have just updated our features in the feature store, but we need to store our targets as well. So what we are going to do is just take this piece of code over here and copy this code, go back to our feature store.py file, and we don't need to update everything, we just need to replace that first part here. Paste it in, and you can see that we have now added a new parameter, targets, which is a Boolean value, and if this value targets is true, it will actually just run this little pipeline over here, which saves the targets to a separate targets path. All right, great. Now that we have this one in our file, we copy the actual execution of this function, insert a new code cell, put it here. And again, just a quick heads up, we need to restart our whole notebook in order to make it available for this runtime. So restart, run all, and you can see that targets got updated in the feature store with the latest date. Great. Next, go to our code file. And we also want to update the fetch data from store function, because now that we have targets stored in our feature store, we also want to be able to retrieve them really easily. So go ahead and copy this part over here. And similar to what we just did before, paste it in, but this time in the fetch data from store function. So replace everything, including this first YAML file loading operation. And you can see that, again, we have another parameter here, which is targets as a Boolean value. And if this one is true, then this little piece of code here gets executed. Okay, and with that, let's go back to our training notebook, insert a new code cell, and also include this little one-liner here to fetch data from our store. And restart the notebook, go ahead, run all, and there we go. This is how we can easily retrieve now targets also from our feature store. By the way, right now I'm storing features and targets in one feature store. There are also other approaches to do that. You could store them separately, or you could store them in one single place. The only important thing is really that you need to be able to treat those two things differently, also with different pipelines. It doesn't matter whether you store them in one place or on separate places, as long as you can apply different pipelines to both of them, you're good to go. All right, back to the code file. So grab these 3 lines of code, go over to our notebook, and paste it in here. What this is doing, it's fetching data from our feature store, target variables from our feature store, and only the ones that are up to the maximum date available in our feature set that we want to train on. And we add that last part over here to make sure that we just extract the targets that are up to the latest available date as in our feature dataset. So run this one, and you can see that we now have target data available onto March 31st. So there's one more thing we need to do, which is to turn this into a list, because it turns out we have 3 target variables. That means what we are going to do is to create and train an individual model for each of these target variables. And now that we paste that in here, we can turn our data frame with the 3 targets and 3 separate columns into a list that is an array of 3 different values. Why do we need to do this? Because we need to essentially train a model for every target variable that we have. And this way, it's just easier to iterate over these 3 different target variables. Okay, so let's scroll down. And in the next step, we will finally grab the code for training our XGBoost model. Let's go over to our code file, and we will find the code for importing and then training XGBoost over here. So follow along and copy this script, go over into the new code cell, and then paste it here. Let me quickly walk you through what this code is doing. So first of all, we are importing XGBoost, and then we loop through 3 different training runs. So 1 training run, 1 model training for every target variable that we have. And this is actually the most important or most critical part of the whole training process, because here we specify the parameters that XGBoost should be using. Now, tuning these parameters and finding the optimal set of parameters for XGBoost could be a course in itself. I gave you some high-level important parameters that you can feel free to tune if you want to, for example, using techniques like grid search. What I will do, though, and I also tend to do that very often in practice, is just to use the default set. So I'm not specifying any parameter here, but my baseline actually is to just let XGBoost figure everything out by itself. And it normally gives you a pretty good baseline to work with. And then from there, you can still try to improve that by tuning even more parameters. The only parameter that we are really tuning is the number of boosting rounds. So the number of boosting rounds is, in layman's term, defining how often XGBoost will try to minimize the loss function, meaning trying to build better models. And at some point, there will be a point in time where there are no further gains, so it has to stop the training. And the good thing is we can provide this parameter here, early stopping rounds, in this case 10, which roughly means that when there's no further gain in accuracy after 10 rounds, it will just stop the training process, even if we had specified, for example, 900 boosting rounds here. I'll show you how that plays out in a bit. So this is the loop for the cross-validation, because especially since we have so few data points, we need to make sure that we shuffle through our training set and make every slice sometimes a test set and sometimes a training set, so we don't overfit our model on the given data. So let's run this code and see what happens. So we can see that here in this case, we got an RMSE of 7,400, and these are the actual unit values. So that's a good thing about RMSE. It's very interpretable. For the second model, we got 7,771 and 6,680 for the last model. So this one here is actually the best one. But let's take a look visually how that turns out. Let's head over to our code file, and we want to get some experience on how to use it to make some actual predictions. So open this notebook inference.ipynb and open the code along file. First of all, let's import the necessary libraries here that we're going to need. Also bear in mind we're using our feature store and feature processing functions from the previous videos. And then next, set the path to the YAML file. Over here, let's quickly grab that, paste it in, and run it. And now we are ready to pull some data from the store for which we want to have some predictions. So in order to do this, take this code, paste it here, and this is just calling our fetch data from a feature store function, given a certain date and every data that comes after that. So we run that, and you can see these are our features for this given date and all consecutive days after these. Great, so now we can run predictions from these for all three models. And for this, we just need this prediction code, which is really short. And again, it's a loop. We're basically iterating through all the models, calling predictions for each and storing that to a list. And let's see how that list actually comes out. So there you see, we have 3 arrays, and every array contains a list of predictions for the given batch data that we just fed to the model. So with that, let's move on and see how our predictions were actually performing. So grab the code to get the true target values. And because this was a batch scenario where we already had the target values, you can just compare to the real values and see how that looks like. So there you go. These are the target values. Of course, it's a bit hard to compare them. So let's pull our predicted values next to these. And this is how we do it. A little code over here. Insert that below. And what it does is it joins the predictions to the target values, so we can just compare it and see how it goes. And again, in this case, you would probably not run the predictions for all these historic data sets, because in the real world, maybe you would already have that data. But this is just for comparison purposes, so you see how the model is working and how it's actually comparing. And it might be hard to just look at this huge table of numbers here. So an even better way to visualize that is, of course, using a little chart. So let's go ahead and just do that. We have some code here that is producing a little plot for us where we can now specify a time, for example here, and then what we'll get as a result is a plot that compares the actual value, which is the blue line over here, to the predicted value, which is this red dashed line over here. And now you can go ahead and see, for example, how the model is also performing on data that was not part of the training data. Remember, we only trained until March 31st of 2024, and now we have some out of sample predictions. The advantages and disadvantages of batch forecasting systems. We'll also compare them to near-time and real-time systems to help you understand which approach best suits your needs. So let's go. First, let's recap some basics of batch forecasting. These systems process large volumes of historical data in batches, and they generate forecasts at regular intervals, such as every hour, every week, every day, depending on your use case. Batch forecasting is typically used for more long-term planning and more strategic decision-making. One of the key advantages of batch forecasting is its ability to handle and analyze large historical datasets. This allows you to capture long-term trends and patterns. Additionally, batch forecasting benefits from a large sample size and, of course, more data points, resulting in more accurate and reliable forecasts. Another advantage of batch forecasting is its computational efficiency. What does it mean? Well, by processing data in batches, you can optimize computational resources, for example, by scaling them up just as needed. This makes batch forecasting suitable for complex models and algorithms. Moreover, batch forecasting is cost-effective as it requires fewer computational resources compared to real-time systems and can be run on cheaper hardware, for example, during off-peak hours, like overnight. The job might take a little longer to complete, but it wouldn't really bother you, because no one's there anyway. So, let's take a look at some of the disadvantages in batch forecasting. One of the main drawbacks is latency. Since forecasts are generated at fixed intervals, they may be not suitable for use cases that require immediate action. Additionally, batch forecasting has limited responsiveness to recent events. For example, it cannot quickly incorporate the latest data points or events, which means it may miss out on capturing sudden change or anomalies. Another disadvantage of batch forecasting is data staleness. So this means the forecasts are based on historical data which may become outdated over time and not reflect the current patterns or trends that are actually going on. And furthermore, batch processing generally involves data transfer and storage overheads because you have to move the data physically from the point where it's generated to where it's stored, typically in a data warehouse. Next, let's talk about near-time forecasting systems. We will cover them in even more detail in the next chapter, but here's a little preview. These systems process data and generate forecasts at frequent intervals, like every hour, minute, or even every couple of seconds. Near-time forecasting strikes a balance between batch and real-time systems. It's suitable for applications that require frequent updates but don't need real-time responsiveness. On the other hand, real-time forecasting systems process data and generate forecasts as soon as new data arrives. We will talk more about real-time systems in Chapter 3, but just so you get the gist of it, real-time systems provide near instantaneous predictions as your data comes in, similar to a reflex. That makes these systems suitable. Welcome to our first challenge. Open the file challenge.ipynb and see if you can answer the following question. How would you add another feature which is categorical, such as the day of the week? When working through this exercise, consider the following questions. How would you calculate this feature? How would you represent it in the data? Where would you store this feature, and how would this feature affect your pipeline? What would you need to rework? If you need some help, there's a code along file over here, which contains the code for this exercise. So let's take a look at the solution for this exercise. Quick heads up, there are different approaches to that, but here's the one that I took. First of all, we need to calculate our data to a daily level, just as we did previously. All right, so that's how I did this over here. Next, we need to represent our day of week in some kind of numerical representation, so our model can actually work with that. So there are two ways to it. The first way is to encode it as a numeric variable, which is not necessarily ideal, but it's the most straightforward way. Just quick heads up that by encoding it to a numeric variable, it's still a nominal scale, not a ratio scale. So actually you're not allowed to do any ratio operations on them, but it gets the job done in a lot of cases. So that would be the most straightforward approach, to just convert that into a numeric scale where, for example, 0 is encoded as Monday and one as Tuesday, and so on and so forth. So every data point here, every weekday has a separate label. The second version would be to use one-hot encoding or dummy variables. And this really makes more sense if you have, for example, categories that need specific parameters for each category. Because what's happening now is that every category level of your categorical variable becomes a new column. And that means for every new column, you can train a new parameter. So your model will be better able to handle the deep intricacies of this data. But quick heads up, it also comes with a big disadvantage. That is, if you have a lot of categorical data, then this will increase the dimensionality of your data, making it more likely to overfitting when training an advanced model on it. So let's store our new feature. In our case, I just chose the most straightforward approach to encode it as a numeric variable. So again, in this case, I would just recalculate the whole feature store and save it as a separate version. In a real-life scenario, you would not recreate the whole feature store, but just create a new feature for a given entity, and this entity will be a period in time, and the new feature will be the weekday for it. If you're using a library like Feast, for example, or any other feature store software, this will allow you to just create a new feature view instead of recreating the whole feature store for your batch data. But here, to keep things simple, I'm just defining a second version of the feature store. And here, this is the only thing I changed really. I added the day of week, and it's an integer value because I just used the numeric encoding. So now we can update our YAML file, and now we also need to update our feature pipeline by adding the new calculation to the feature pipeline. And again, this is all the same that we had before. The only new addition here is that we now additionally have the day of the week column, which we just take as this day of week calculation here from pandas. So let's run this one. And next is that we need to populate the feature store with the data from the new pipeline. So rebuild the feature store by running this one. And you can see now it got updated with the latest value. And of course, now that we have updated the feature store, we also powerful approach that can be sufficient for many business needs. First, let's define what we mean by near-time. A near-time system processes and delivers data with a slight delay, typically ranging from a few seconds to a few minutes. It strikes a balance between the immediacy of real-time systems and the batch processing of historical data. That makes near-time systems very suitable for many business cases where a small delay is acceptable. Now, let's look at the characteristics of near-time systems. These systems process data at frequent, regular intervals, such as every few minutes. They provide results or insights with a short delay. And to do this, near-time systems often utilize micro-batch processing techniques that offer a compromise between latency and computational efficiency. So when should you consider near-time systems? One scenario is when you need frequent data updates, but you don't necessarily need to trigger actions immediately. Tracking website traffic, for example, can often be done effectively with near-time processing. It's nice to see how many people are currently on your website, but whether this data is delayed by a few seconds typically doesn't matter. Another situation is where the given delay is acceptable for your business case. Popular item recommendation is a good example. You might recommend items that were popular on your platform within the last hour or so, instead of knowing what's being sold right now. Cost optimization is another factor to consider. If the cost and resources required for a real-time system are not justified by the business benefits, near-time processing can typically be a more cost-effective solution. And additionally, near-time systems can handle large data volumes and more complex computations, especially across many different data sources. Let's look at some examples where near-time systems are commonly used. We already briefly touched some of them. Several things you need to consider. Among the various requirements, we'll focus on 4 critical aspects: infrastructure requirements, data requirements, model requirements, and monitoring requirements. Each of these play a crucial role in building a robust and reliable near-time forecasting system. First, let's talk about data requirements. One of the most important considerations is data availability. You need to ensure that the necessary data sources are accessible in near time and that your data pipelines are ready to ingest and process that data quickly. Additionally, data quality is paramount. Implement data quality checks and validation mechanisms to handle anomalies, missing values, and outliers effectively. Continuing with data requirements, data consistency is another key factor. Can you maintain data integrity during near-time processing across various sources and systems? If not, you might not be ready for near-time forecasting yet. And lastly, consider data latency. Your ETL processes should be able to handle data processing quickly enough to minimize latency and allow for timely storage and consumption. Next, let's discuss model requirements. Model performance is a critical consideration, as there's often a trade-off between model complexity and prediction speed. You may also need to consider model scalability, especially if distributed computing is necessary. Model adaptability is another important aspect. Ensure that you have processes in place for retraining your models as new data arrives. And finally, depending on your use case, model interpretability may be a requirement to keep in mind, especially if you need to deliver this interpretability right at the time of prediction. Moving on to infrastructure requirements. You will need to provision sufficient computational resources at the time they are needed. Storage systems should be able to handle large volumes of data and support fast read and write operations. If you can, use in-memory stores for faster processing. Reliable and fast networking connectivity is also crucial to ensure smooth data transfer between data sources, processing, and consuming applications. And lastly, fault tolerance is essential. Implement redundancy, backup processes, and automatic failover mechanisms to minimize disruptions in your near-time pipelines. Also, it's not only about starting things up, but also about keeping things running. Monitoring requirements are therefore equally important. Automated logging mechanisms will help you track key performance metrics Imagine this scenario. Instead of processing our data once every day or night, we want to process it every 3 hours based on our latest data to predict energy demand for the next 24 hours. So how do we do that? Let's take a look at how we would need to recalculate our features. Go to the code along file, and first of all, let's import some data. In this case, the main difference here is that we have a cutoff of this data at some random point. You can see the latest data point that we have here is around 2 p.m. So these are not full batches of daily data, so just a fraction of daily data that we just get here. So let's see how we can now update our feature processing pipeline for this. First, we are going to create a new feature store in order to make sure that we can add a new feature pipeline for this one. As you can see here, right now, our feature store has a minimum offset of 13 days. That means we need to have at least 13 days of data in order to calculate the current features for our model. So let's translate that into hours. What would that be in hours? We take this code and run this one. And you can see we take the maximum offset, multiply it with 24 hours, and we actually add one additional day. Why do we do this? Because we need the current data point as well. We have the current data point in time and then 13 consecutive days of data, and that translated into 24 hours. So in total, we need 336 hours of data. So let's create this data set by taking this code. And this is what we call our mini batch of data. So the mini batch of data is really just our data, most updated data with the maximum offset of hours. So in this case, 336 rows. So starting at the latest timestamp we have, 2 p.m. on April 4th, and then going back until March 21st at 3 p.m. All right, now we can use this data set to calculate our feature set. And in order to do this, we need to rethink our approach to how we calculate the feature, because remember previously we just resampled our feature by day, and this doesn't work because we don't have complete days right now. So what we do instead is we resample at a 24-hour interval, and we need to rewrite some custom code in order to do this. So we define a custom chunk size, which is 24 rows of data. Every row is 1 hour. And then we slice our data accordingly and resample it based on that 24-hour interval. And as you can see, what we get as a result is a data frame which looks similar to our feature data frame before, but not sampled on a daily basis, but on a 24-hour basis. But still, it contains 24 data points for every aggregated value here, which is the sum of the energy demand. All right, now that we have created this new resampling strategy, we need to However, there's a natural limit to how often we can do this. There are two main factors. Factor one is the overhead for data read and write operations. Let's take a look at the code. This code has just the part in it for the data I/O, where we fetch our data from the CSV store, could also be a SQL statement fetching your data from a data warehouse, and filter it given our minimum data offset. It also comes with a timer that tells us how long this process took. Let's run it. You can see that in this case, it took just about 0.008 seconds. But bear in mind, this is a very, very little data set. In real-world scenarios, even a near-time scenario might require you to physically move lots of data in your mini-batch from one location, like a data warehouse, to a different location, like a microservice that is calculating the features. And while you can try to minimize this load, you can't fully eliminate it, because the read and write operations, they take their time. The second big factor is the time it takes for actually calculating your features. Let's grab some code over here. You can see we're talking about our feature processing pipeline right now, and it also comes with a timer. And usually that's a little faster than the data I/O. But again, the size of the small data set here really brings this very close down to zero. Remember, our goal is to predict the next 24 hours of energy demand given the most recent data that we have. Let's simulate new data coming in. Insert a new code cell, go to the code along file and copy this block of code over here. Paste it in, and again, what this is doing is just importing our scripts, importing our YAML file, defining a date time which was not in the training dataset, and then applying our mini batch function where we just select the latest offset of hours required for online prediction. And that's how our feature dataset looks. Great, now let's load our model. Go over here, copy this code, and paste it there. And let's run our prediction. So you can see this is the prediction, the next 24 hours of energy demand given this data set over here. How well is this prediction? Well, let's find out. Go over to our code file, copy this, and paste it here. So this code loads the next 24 hours of data. Now, open this file here, end-to-end.ipynb, and open the code along file. In here, you can just copy all of the code and then paste it in here into a new code cell. Before we run this code, let's walk through it really quickly. This script covers essentially 4 steps. So in step 1, we define the configuration variables, such as our YAML file over here, or the data for which we want to request new predictions. And also we define the maximum offset hours for our feature calculation, which we take from the YAML file. And then we move to step number 2. In step number 2, we define the source to the incoming unprocessed data, which typically would be from a data warehouse. And then we query our mini batch by using the given datetime and the maximum offset hours needed. And finally, in step number 3, we calculate our online features for near-time prediction. Bear in mind that this feature calculation is never stored. Updating our feature store is often too complex for a near-time scenario. So we typically leave feature store updates in the regular batch process, which could, for example, run every night. And there, it could still sample our data every full hour. Also, we could retrain our model during this batch workflow, which makes the whole handling just much easier. So what's left is step number 4. So goes our prediction. So you can see we can just run this process, for example, now on a scheduled basis, for example, every 3 hours or so. And then we could use the prediction results either immediately for better decision making, or we can store these predictions to a database so we can access them once we need them. Especially in comparison to batch processing, so you get a better understanding of when to use which approach. As a quick recap, near-time forecasting systems process data and generate forecasts at frequent intervals, such as every hour, minute, or even second. They provide almost real-time insights using a batch forecasting stack. which makes them a good fit for many applications that need timely information but don't necessarily true real-time responsiveness. One of the key advantages of near-time forecasting is the ability to provide timely insights that can be used for timely decision-making. By incorporating recent data into the forecasting models, near-time systems can also capture evolving patterns and trends, potentially improving accuracy compared to traditional batch forecasting. Another benefit of near-time forecasting is that it can often be built upon the same infrastructure and architecture paradigms as batch forecasting. This means you can leverage your existing tech stack and gradually scale up the real-time forecasting as your business needs evolve. However, near-time forecasting also has some disadvantages. One issue is the potential for inefficient calculations. In some cases, a lot of the predictions generated may never be used, such as calculating near-time recommendations for all users on a platform when only a subset of these users are active. This inefficiency is similar to batch forecasting, but it occurs even more frequently. Near-time forecasting also relies heavily on timely and accurate data. Incomplete or corrupt data can reduce the quality of the forecasts, in the worst case without you even noticing it. Additionally, the focus on more recent data may sometimes overrule long-term patterns or trends that could be more important for certain use cases, such as seasonality factors. To compare batch and near-time forecasting head-on, let's look at this table. Near-time forecasting offers high forecast timeliness and low data latency compared to batch forecasting. However, it also comes with higher computational complexity and infrastructure cost. So some typical Welcome to our next challenge. This time, we want to add another dataset to our forecast to make it a truly multivariate time series forecast. Open the challenge notebook here on the left side, and then explore the instructions for this exercise. In this branch, you will find two files in the data folder: the energy data CSV, which we have already used throughout the course, and the weather forecast CSV, which is a new file. So this dataset contains the weather forecast for a given date hour in Fahrenheit. You can get real-time data like this from service providers like OpenMeteo. That's the one that we've used for this course. Now, your task is to build a feature from this data, integrate it into your batch model training, and update the end-to-end pipeline for near-time prediction for forecasting the next day of energy demand. I know this is a lot to ask. Okay, let's find out how we can solve this challenge. First of all, we load our data files, the energy data and the weather data, and then we can quickly explore both datasets. The energy dataset is pretty straightforward. It's the same that we have used throughout this course. So the weather dataset is a little bit more interesting. You can see two things. First, it comes at the same granularity as our energy data, and second, it also has the same starting and ending points of its time period. And then there's just one column, which is the temperature. So one thing we have to be aware of here is that this is the forecast for this given date. So in order to use that as a feature, we need to introduce a little shift. Because, for example, given this date, 2nd of January, 3 o'clock, we want to have the prediction for the next hour, which in this case will be 4 o'clock. So this value here, minus 15.6, would need to go up and be here. And you will see that in our feature processing pipeline that we can do that with a very simple Shift command in the preprocessing script. So let's continue. First, initialize our new feature store so we can save those features also somewhere. We define this as v3 and we add our new feature over here, temperature forecast, which is in this case type float. Next, let's update our feature pipeline. In this case, our feature pipeline takes two data frames, the energy data frame and the temperature data frame. The beginning is really unchanged to everything else that we had before, but here we have a new addition. Now we add the weather data. First of all, we introduce the shift that I just explained to you, and then we bring the weather data to the same granularity as the energy data. Remember, it also came in hourly batches, but now for our batch features, we need it aggregated to a daily level. So that means we are also resampling it here on the daily level, and to aggregate these values we are using the mean, which gives us the average of a 24-hour interval. And then we can join our weather data set to our energy data set and just rename the column from temperature to temperature forecast. We drop the missing values and that's our feature pipeline. So we can test this new feature pipeline, and as you can see we have now the exact same values as before plus a new temperature forecast here in the end. Great. Next step is to update our feature store. So we apply our pipeline and then we update our feature store so the batch features are stored here. And now we can use these batch features to train our model. And to train our model, we just run the same code as before. We define our training data, we define our target labels, and then we run the overall training. In this case, because we're just trying to predict the next day, I'm not running through a training loop that trains 3 different models, but just one model for the next day. So we run through this whole process, including cross-validation, and in the end we get a test metric here of 7,401 for a root mean squared error, which is more or less the same that we have before. So let's inspect our learning process. You can see that the early stopping here kicked in already after 8 rounds of boosting. So this tells us really one thing, which is we don't have enough data. And that's pretty obvious because we just have 78 rows of data. Now we're adding even more features, even more information to it. And to really leverage that, we would really need to have more data. But in any case, let's train on the full data set just for the sake of this example here. And as a result, we would get this XGBoost regressor model. And let's take a look at the residuals. So when we take a look at the residual plots, you can see this graphic here. And this really shows us that now we have this trend where the model over predicts higher values and there are situations where it may not be enough. In this section, we'll explore scenarios that might be best served by a real-time forecasting system. So what is real-time forecasting and how does it work? Real-time systems process and deliver data immediately upon request, with delays measured in milliseconds. To make this work, we typically handle incoming data through a streaming processing framework, like Apache Kafka, from where other services can pull this data as needed. One of these services could be an online feature pipeline that generates the features for our forecasting model right from the stream and stores them in a so-called online feature store. An online feature store is really a dynamic repository to manage and serve features for real-time predictive models. Systems like this are ideal for applications that require instant actions on the most up-to-date information available. Real-time systems have a distinct set of characteristics. They process data as soon as it arrives, typically using time window aggregations to generate features. Predictions are calculated on demand. That means providing insights based on the latest available data. And to achieve real-time performance, we typically need to leverage technologies like streaming services, in-memory computing, and distributed systems, where computational complexity heavily depends on the specific use case. It can range from pretty simple applications involving just a few data sources to super complex systems serving millions of users with data from hundreds of different origins. So when should you use systems like this? One situation where real-time forecasting is crucial is, of course, in time-critical applications. When decisions or actions must be taken instantly based on the latest data, real-time systems are often unavoidable. Imagine, for example, a scenario where we want to generate personalized next best offers based on the latest user activity data, or providing up-to-the-minute weather forecasts. Another scenario where real-time is essential is when data freshness is more important than data completeness. In some cases, the most recent data points have the highest influence on the prediction result. For instance, if you want to predict the next relevant video for a user to watch, knowing what they just finished watching might be more relevant than the entire watch history. Real-time forecasting is also beneficial when predictions are needed for specific subsets of data only. This is very typical for large online platforms. Instead of running predictions for every user, real-time systems can calculate recommendations or forecasts only for active users, or based on specific requests, which is more efficient and cost-effective. And additionally, real-time forecasting is ideal for personalized and context-aware applications, where forecasts need to be tailored to individual users or specific contexts in real time. Let's look at a few examples where real-time forecasting is commonly used. As we have already seen, e-commerce is a popular area. Just like with near-time systems, we want to focus on 4 requirement categories: infrastructure, data, models, and monitoring requirements. Let's start with data requirements. One of the most critical aspects is real-time data ingestion and processing. If your data isn't available in real time, you can't do real-time forecasting. Your systems must support streaming data pipelines and real-time data connectors accordingly. The second big requirement is data quality. In real-time setups, you have no chance to check your incoming data quality manually. That means you have to have mechanisms and systems in place that perform things like data validation, cleaning, and anomaly detection automatically. This alone can be really challenging. Another important data requirement is low latency data processing. That your data is available in real time does not necessarily mean your data processing is fast enough for real-time needs. You typically need to leverage concepts like stream processing, in-memory processing, and edge computing to help minimize latency and enable real-time workflows. Data scalability is also a key consideration. The system should be able to handle high volumes of real-time data, which often requires horizontal scalability and distributed data processing architectures. Moving on to model requirements. The ability of your model to generate predictions in real time is paramount. That's why models used in real-time forecasting systems must be fast and efficient. When it comes to retraining or updating your model should allow for incremental updates that lets it adapt to new data in real time. When serving a large amount of users and processing a lot of data, your model needs to be scalable as well, meaning being able to run on a parallelized architecture that allows flexible horizontal scalability. And depending on the use case, model interpretability may also be necessary. Some use cases just require fast predictions, but other use cases, like credit risk scoring, need fast and explainable predictions with real-time feature importance calculations on the fly. Let's look at infrastructure requirements. Real-time systems require a completely different tech stack compared to batch and near-time systems. For optimal performance in a real-time forecasting system, you might deploy edge computing for immediate data processing close to the data source, but leverage serverless architectures to manage variable data integration loads efficiently. When it comes to storage, real-time ready solutions like in-memory databases, key value stores, and time series databases allow for fast data access and retrieval. Real-time communication protocols such as event-based processing and gRPC facilitate efficient data exchange between system components. Also, scalability and fault tolerance in these settings is also critical, ensuring that the system can handle varying demand while remaining resilient to failures. Next, let's briefly look at monitoring requirements. They are really essential to ensure smooth operation of real-time forecasting systems. Real-time monitoring and alerting capabilities, including metrics, logs, and automated monitoring, enable proactive issue identification and resolution. Real-time model performance tracking, covering aspects like accuracy, latency, throughput, and resource utilization, help maintain optimal system performance. And continuous testing and validation, often implemented through CI/CD. Today, you will learn how to set up a real-time data stream in Kafka and QuickStreams, which is an excellent library for manipulating streaming data, very much similar as your use from Pandas. To make everything as smooth as possible for you, I have loaded up a Docker image here for you. This Docker image spins up all the resources you need for completing this exercise. To start the Docker container, make sure you're in the real-time directory, and then launch the container using Docker Compose up-t. Now this will launch the container, and if you do this the very first time, this will take some minutes. Once everything is complete, click here on the Ports tab, and you should see that port 9021 is forwarded. If this is not the case, go to Add Port and add 9021. As you can see, we already have it here, so let's go over here and click this little icon here to open the control center. Now this will normally open a little GUI from Confluent Kafka that lets you monitor your current streaming service. If you get an error like this here, don't worry. It just means the GUI isn't ready yet. It might take 2 or 3 minutes to load. We'll check back later. For now, open the file dataproducer.ipynb and also close that so we can see a little more. So there's quite something going on here in this file. So let me quickly walk you through this. The first section is the application setup. In this section, we import the necessary libraries and set up a streaming application that connects to Kafka, our message broker. The application runs at a specific address and under a given consumer group. And here we define the name of the topic under which this application should handle our data. I called it incoming data. So if you have never worked with streaming data before, this is how data is being organized. In streaming data scenarios, data is organized around topics. Think of a topic like a category on a message board. Messages are continuously posted under this category, and anyone interested can fetch these messages. So part 2 simulates the incoming data. For this, we will stream data from two CSV files, an energy dataset and a weather dataset. To keep things simple here, we will just alternate between sending messages from the energy data and the weather data. And there's a little sleep timer in between, just to make sure that we simulate a more natural real-time flow of the data. But of course, in a real-time scenario, these would be two different processes. So every data source would submit data as it becomes available to the topic. And then finally, part number 3 ensures that all pending messages are pushed out to the topic by flushing the producer script. Now, let's run this to see it in action. We will build an online pipeline that listens to incoming messages, applies our window function, creates our features, and stores them to a new topic. But first, let's launch our Docker container. Type docker compose up and d. And once the Docker container is running, go to the data producer script and also run it. Make sure the data is being produced to your stream. Now let's open the file featurepipeline.ipynb. This code will generate our online feature store. Quick context, I changed our scenario here a little bit to adjust for the real-time scenario. Let's say in this real-time setting, we want to predict the energy demand not for the next 24 hours, but just for the next hour. I updated our features for that, and I'm using a different model. But let's go through this code section by section. The first function, passPeriod, is a utility function to make sure we can pass the date timestamps correctly, since both the energy data and temperature data timestamps are formatted differently. The second function is also a utility function that helps us to calculate the lagging as needed for our energy features. Next is where really the meat is of this whole pipeline. This function takes a message from the stream and tries to parse the period information and turns it into a feature record ID. If the value of the message is energy, then the feature processing for energy data will be applied. This also includes the rolling time window calculations. The calculation will then be stored to an online feature store with the given feature record ID. If the type of the streaming message is temperature, then we will write this value along with the respective feature record ID to the stream as well. And lastly, we run this whole process. But before we do this, let's verify two things. First, open our port 9021 and see if your Kafka service is running correctly. Under incoming data, you should see a message stream of data being sent to the incoming data topic. If this is the case, go back to the feature script and run it. You will see that it's now waiting for incoming messages and process the features as new data is becoming available. Let's see how that looks in action. Go to the control center, select topics, and you can see a new topic. data to a real-time stream and calculate our real-time feature store, the last missing piece is to make predictions. So let's see how that works. First off, make sure your Docker container is running from a fresh state. Go into the real-time folder and launch your Docker container. Be sure that here on the left side there's no state folder, and then go to the data producer script and run it to produce some data. Once this is running, go to your feature pipeline and also start your feature pipeline so it's listening to the produced data. Now with that, let's close our terminal for now and go to the inference notebook. What we will do here is to define a Kafka consumer to subscribe to messages in the feature store. This one isn't using quick streams anymore, just Confluent Kafka. Let's take a closer look. The function fetch all feature records is, as you might guess, fetching all feature records from our online feature store. The way this works is that we will always pull the latest data from the feature store based on the last time that we have checked. So it's actually not pulling literally all features, but just all features that became available since the last time we pulled that topic. The function will continue pulling data from that topic until a timeout of, in this case, 1 second is reached. Now, the threshold of this timeout really depends on the velocity of your data coming in. If the timeout is too high, this function will run forever because it won't stop listening to your data. If the timeout is too low, it might miss some of the updates. So keep this in mind for now, but we will talk about latency considerations in more detail later. For now, let's define this function and run it to see what we get. So you can see that we still don't have complete features here, just features from different parts of our source dataset. The way you need to process this data really depends on your use case. In our use case, we just want to predict the next hour of energy demand given the latest data. So what we will do is we will just group this data frame by message ID, merge them so that the NA values get overwritten. We sort it and then find an example of our real-time forecasting pipeline would look like. But before we start, some housekeeping. In order for this pipeline to work, we really need to start from a clean state. Make sure that your Docker container is running and your Kafka service is ready to receive data. The easiest way to check this out is to click on ports and then opening your control center by clicking on port 9021. So in this control center, there should be no topic. If you see any topic like here, go in, copy the topic name, and delete the topic. Do this for all the topics in here. Great, now your Kafka stream is ready for this exercise. Go back to your code space and open a new terminal. Make sure that you are in the real-time directory. Then run the producer script. Next, open a new terminal and run the feature script. Quick heads up here. If you go to the producer script, you will see that the timeout has been reduced from 2 seconds to 0.2 seconds and 3 seconds to 0.3 seconds respectively. So that means data is now coming in at much faster pace. Check your Confluent control center by refreshing the page and see if your data is coming in nicely in the feature store. If that's the case, we can now start calling predictions. Return to the code space and You've experienced firsthand how we handle data with millisecond updates in our demo environment. But what happens as we scale this up? With real-time streaming systems, like the ones we've been using, we can indeed scale our data throughput almost infinitely, at least theoretically. This is made possible by the concept of horizontal scalability. As throughput increases, we simply add new compute clusters to our pipeline. This allows us to process literally terabytes of data while maintaining millisecond latency. But there's also another side to it. Increasing our data throughput does introduce a lot of new challenges, particularly with data integrity and veracity. More data moving quickly will typically lead to more errors, such as incomplete records or corrupted data, which can really have a bad impact on our forecasting model's performance. Garbage in, garbage out, as the saying goes. To ensure that our forecasts are reliable, we need robust systems. Let's discuss the advantages and disadvantages of this system over batch and near-time systems. First, let's look at some of the advantages. As we have seen, one of the key advantages of real-time systems is the ability to provide instant insights and actions based on the latest available data. This allows businesses to respond quickly to changing conditions and make timely decisions. Real-time systems also enhance the user experience by delivering up-to-date information and offering a more interactive and context-aware experience. Another benefit of real-time systems is increased efficiency and productivity. By serving predictions only for instances where they are actually needed, real-time systems optimize resource utilization. Additionally, adopters of real-time systems can gain a competitive advantage, especially in more traditional businesses. If you're using real-time systems to respond to market changes and customer needs immediately, chances are you're really ahead of the curve and have an edge over your competition. However, real-time systems also have significant disadvantages. One challenge is the complexity and development effort involved. Designing, developing, and maintaining real-time systems is for most organizations more complex compared to batch systems. It also requires specialized skills and expertise, which you might not have yet in-house, and learning these systems may involve a steeper learning curve for your teams. Moreover, the streaming paradigm might overwhelm organizations that are not prepared for these increased infrastructure requirements. Data quality and consistency are typically also major concerns in real-time systems. Incoming real-time data is often incomplete or inconsistent, requiring pragmatic approaches to data validation and cleaning, because you simply can't control everything 100% like in batch scenarios. Again, that's something your organization might just learn to tolerate. In terms of operational complexity, maintaining system compliance, documentation, and keeping service-level agreements adds additional layer of complexity to real-time systems. Let's quickly compare near-time and real-time systems across various dimensions. Real-time systems offer a high forecast timeliness and provide predictions immediately on demand. Near-time systems also have a high timeliness, but they operate on a scheduled basis. Also, real-time systems have lower data latency compared to near-time systems, but the scalability and fault tolerance requirements are usually much higher. When it comes to computational complexity and infrastructure cost, it really depends on the use case, which approach is more challenging. If you're dealing with few data sources and many users, real-time forecasting systems might actually be easier and cheaper to run than near-time systems. However, for more complex data integration pipelines, near-time systems usually turn out to be cheaper and less complex after all. At this point, you might wonder, do I actually have to choose between batch and real-time processing? Can't I just have the best of both worlds? And the answer to this question is yes, you can, using an approach called the Lambda architecture. The Lambda architecture is a design paradigm that lets you handle large quantities of data by combining both real-time and batch processing methods. The main idea here is that incoming data gets processed So here's our final challenge. Open the challenge notebook. Real-world data is messy, and real-time data even more so. So that's why every real-time pipeline needs robust systems to handle data errors. And in today's challenge, you will implement a simple anomaly detection mechanism in your feature processing pipeline. Check out the file producer.py. The file has been modified so that every 40 to 60 messages, an anomaly is being introduced, which includes data that is 2 to 3 times higher than usual. Now, your task is to detect this data. For this, review the feature processing script provided below. It's exactly the same that we used previously, unless for this little tiny detail here. It comes with a new function called detect anomalies. So here's where you would need to implement the logic for the anomaly detection. How would you detect the anomaly? Small tip, the rolling mean and the standard deviation of your incoming data will Okay, let's see how we can solve this challenge. There are certainly different approaches to this, but here's the one that I found most practical. My approach relies on comparing the current data point against the 7-day rolling average and standard deviation of the incoming data, because that's information that we are calculating anyway for our feature. So let's see how this looks like. According to this implementation, the current length of our rolling window must be at least 7 to work. If this is the case, then we will calculate the rolling window average and the rolling window standard deviation just as in our feature set. Now, if the incoming value lies outside the mean plus a given threshold times the standard deviation, we will flag this as an anomaly. By default, my threshold is 2 times the standard deviation, but you could of course also update this depending on how sensitive you want your anomaly detection to be. And going down, this is how my print function looks. It simply grabs the current value at the given period of the observed data point and batch or real-time data. This final chapter will help you understand why continuous model evaluation is important and introduce you to the different strategies and metrics tailored for each system type. Model evaluation plays a vital role in assessing the performance of forecasting models and making informed decisions. It helps in selecting the best models, tuning hyperparameters, and monitoring model performance over time. It's important to note that batch and real-time forecasting systems require quite different evaluation strategies to effectively assess and maintain model performance. When it comes to evaluating time series forecasting models, there's a set of commonly used metrics. For example, the mean absolute error, which measures the average difference between your forecasts and the actual data, treating all errors the same way, no matter their size. Then we have the mean squared error, which squares these differences. That means larger errors will have a bigger impact. And then we have the root mean squared error, the one that we have been using throughout the exercises. It's simply the square root of MSE, making it easier to understand because it's in the same units as your data. And then we have percentage errors, which are another class of metrics used in time series forecasting evaluation. The mean absolute percentage error, also called MAPE, calculates the average absolute percentage difference between predicted and actual values. One issue with MAPE is that it can exaggerate errors when the actual values are very small, near zero. To address this, we use the symmetric mean absolute percentage error, which is a variant of MAPE that mitigates this sensitivity by including both the actual and predicted values in the denominator. It's bounded between 0%, good prediction, and 200%, a really bad prediction. Let's look at some key evaluation strategies for batch forecasting systems in particular. First, we have the rolling window analysis, which is also often called the rolling origin evaluation. It helps us test the model on different segments of data over time. This method slides a window of data forward, which allows us to test on the latest available data and mimics how you would use the model in real situations. Then we have time series cross-validation, which helps us to assess the model performance and avoid overfitting by creating multiple train and test splits, often using the rolling window evaluation under the hood. And finally, backtesting, which involves applying simulations on our historical data to see how decisions based on the model's output would have played out in the past. In real-time forecasting systems, evaluation strategies focus even more on continuous monitoring and adaptation. Online evaluation metrics track the forecast error over time intervals, such as the cumulative absolute error or the moving average. It's crucial to keep an eye on drift, which happens when the patterns in the data change over time. This can make your model less accurate. Monitoring drift helps us know when to update or covered a lot with regards to training forecasting models and using them to serve predictions. What we haven't discussed in more detail yet is how and when we should retrain these models. So let's do a quick deep dive into that. First of all, let's clarify the what, why, and how. What is model retraining after all? Retraining a model means updating the model weights on new data without changing the existing model architecture. Think of it as recalibrating it. Why do we need to do this? Well, it helps us to maintain performance and capture recent patterns in data that were not apparent when we trained the model the last time. And how do we do it? Well, this depends whether we are talking about batch or real-time systems. Let's start with batch retraining. In batch retraining, we typically establish a regular training schedule based on data characteristics and business requirements. Automating this process through workflows and pipelines ensures consistency and efficiency. A good rule of thumb here is to retrain your models at least once per business cycle, be it weekly, monthly, or quarterly, for example. Besides retraining by schedule, we can also retrain our batch models by triggers in drift. Drift is a change in our data distribution, which we can detect in our feature processing, for example using statistical tools like the Population Stability Index and the KL divergence, which are very popular to detect these drifts. As a general rule of thumb, you should define a threshold first and then retrain your model when the drift exceeds that predefined threshold, for example like a 20% change in your key metrics. Let's shift to real-time retraining. In real-time retraining, we could of course just piggyback on the batch training process. That means training our model on a regular schedule and then using this updated model to serve real-time predictions. But in some real-time scenarios, these scheduled updates are not enough. Instead, we want the model to be updated automatically as new data comes in to account for the latest patterns and trends in our data. For this, we can utilize a process often called incremental learning or continued training. Tools like XGBoost allow updating the model with new data without starting from scratch. But figuring this out takes some time because it's very easy to build models this way that overfit. A good rule of thumb, especially when using XGBoost, is to use a smaller learning rate and fewer boosting rounds to avoid this overfitting. Another form to prevent this overfitting is to use a form of streaming data integration, where we don't update our model on every new data point coming in, but instead buffer this data to microbatches that are then used to automatically retrain the model. Think of it as collecting data over a 24-hour interval before using it to continue the training. As a rule of thumb, the buffer size that you should use follows the desired update frequency. So if you retrain your model every day, use batches within a 24-hour time window. Another helpful factor to look at is the feature importance score, especially when tools like XGBoost have that built in. These feature importance scores help you understand which features are the Can you believe how far we have come? Thank you for spending this time with me to hone your time series forecasting skills. We started off with a crystal ball, and now you can actually predict the future. Well, at least to a degree where it's helpful for your business. So whether you work with sales forecasts, demand prediction, or stock price analysis, you now can get started building a robust and reliable forecasting system. But remember, there's always more to learn. The world of time series forecasting is constantly evolving. Dive deeper in the area that is most relevant to your current business needs and job function. If you want to stay up to date with the latest in AI for business, feel free to subscribe to my newsletter and blog. And if you're more interested in the data engineering part of batch and near-time systems, you could check out these LinkedIn learning courses. Architecting big data applications, batch mode application engineering, or if you're more excited about improving your models, check out Applied Machine Learning Feature Engineering. And finally, if you feel ready for tackling real-time systems, then this is an excellent resource to use. Complete Guide to Apache Kafka for Beginners. Keep experimenting, keep learning, and most importantly, keep having fun with it. Who knows, maybe you'll be the one to invent the next forecasting technique. I'm Tobias, and it's been an absolute pleasure being your guide. Until next time, happy forecasting.